Let's say this is me right over here, and I'm drifting through space at a constant velocity relative to any other inertial frame of reference. And so I am in an inertial frame of reference myself. And in fact, I'm going to define my frame of reference by me. I'm going to say I'm at the origin of my frame of reference. So at all times, I consider myself to be stationary, and I'm at the point x equals 0. And we're going to focus on just the x dimension to simplify our discussion. And I have, my oxygen and everything, and food, so no need to worry about me. Now, what I've drawn here are some axes so that I can plot the path of things as time progresses in my frame of reference. And one thing that many of y'all might have noticed is that I have plotted time in seconds on the vertical axis and our position, our x position, in meters on the horizontal axis. And that might be a little bit counterintuitive for a lot of y'all, especially with math backgrounds. In fact, it's a little bit uncomfortable for me. We often prefer to put time on the horizontal axis and position on the vertical axis. So this is a little bit counterintuitive, but this is, our choice is a little bit arbitrary. In math class, we like to think of our independent variable on our horizontal axis, and we think of time as somehow driving position. So that's why we tend to put time there, then we put position there. But you can flip them around, and as we'll get more and more into physics, we'll see, well, maybe we shouldn't necessarily think of time always driving position, or maybe position in some ways are driving time. But we'll get into that. But let's just first get a little bit comfortable with this. So what would be my position over time on this diagram right over here? And you might notice these numbers: 1 second, 2 second, 3 second, and then in meters I have 3 times 10 to the 8th, 6 times 10 to the 8th, 9 times 10 to the 8th. So these are massive, massive numbers, and you could guess where they are coming from. They're coming from the notion that the speed of light is approximately 3 times 10 to the 8th meters per second. But we'll get to that in a second. But let's just think about my position over time in my frame of reference here. So time equals 0. My x position in this frame of reference is 0. I consider myself to be stationary. After 1 second, well, my position is still 0. After 2 seconds, my position is still x equals 0. After 3 seconds, my position is still x equals 0. So I guess you could almost consider my path on this diagram, where I'm plotting time and space, and at least in the x direction, is going to look like, whoops, I can do a better job than that. It's going to look like that. That would be my path on my little time and space axes, or on this little diagram that I have. But let's think about something a little bit more interesting. Let's think about me having a flashlight. So I have a flashlight here, and at time equals 0, I turn on that flashlight. Exactly at time equals 0, I turn on that flashlight. And let's think about that very first photon of light that emits from my flashlight, and let's plot its path on my little diagram here. So at time equals 0, it's exactly where I am. So at time equals 0, its position is 0 meters. But after 1 second, where's my photon of light? And I'm going to put it, and the photon is moving in the positive x direction. So it's moving in the positive x direction with a velocity of c meters per second in the positive x direction. And so after 1 second, it will have moved 3 times 10 to the 8th meters. After 2 seconds, it will have moved 6 times 10 to the 8th meters. And I've intentionally scaled my axes so that now if I were to draw the position of light relative to time, it's going to be at a 45-degree angle. And that's just an artifact of how I've picked my axes. But let's see if I can plot this. So it's going to look something like this. And this is hand-drawn, so it's not going to be perfect. So the position of that photon over time is going to look like that. After 1 second, 3 times 10 to the 8th meters. After 2 seconds, 6 times 10 to the 8th meters. After 3 seconds, we have 9 times 10 to the 8th meters. All right, well, that's reasonably interesting so far. We're getting a little bit comfortable with my little diagram here. Maybe some of us are getting a little bit more comfortable with time on the vertical axis and my position on the horizontal axis. But now let's introduce another character who could almost define who could define their own frame of reference. So let's say that right at time equals 0, a spaceship passes me by. So I could draw a bigger spaceship than that. So there you go. That's the spaceship, and in the spaceship I have my friend. So that's the spaceship, and the spaceship is traveling with a pretty incredible velocity in the positive x direction. So I guess if this vector is the speed of light, which seems like an awfully short arrow, but if I'm going to say that's the speed of light, then let's say that this thing is moving with half the speed of light, which is still incredibly fast. So the velocity, the magnitude of the velocity here is 0.5 c. So let's plot, and my friend is stationary in that spaceship. The spaceship is moving at this constant velocity, 0.5 c in the positive x direction. So they also are in an inertial frame of reference because it's at a constant velocity relative to me, which is an inertial frame of reference. And so let's plot her position on my little diagram. So at time equals 0, she's exactly where I am. She's at the origin of my frame of reference. Her x position is 0. Now after 1 second, she's moving half the speed of light. So after 1 second, she would have gone 1.5 times 10 to the 8th meters per second. So she would have gone about that far. After 2 seconds, she would have gone as far as light would go in 1 second, because she's going half the speed of light. So she would go about that far. After 3 seconds, she will have gone 4.5 times 10 to the 8th meters. So let me put that right over there. And you see where this is going. So if I were to plot her path, it would look like this. It would look like this. Path of my friend. That's the path of my friend right over there. And I want you to just kind of think about this a little bit. Think about how these different lines are, what they represent. Once again, get familiar with the t on the vertical axis. But now in the next video, we're going to use this, what I just drew, to draw her frame of reference, to draw a coordinate system, or I guess you could say a space-time diagram for her frame of reference on top of this one. And at least in the context of this video and the next few videos, we're going to assume a Newtonian world. We're not going to get to Einstein and special relativity. We're just going to assume, we'll get to that in the next video.